The title for this discussion is From Design to Occupancy, Strategies to Enhance Building Performance and Prediction Accuracy. I'd like to condense all these objectives into two basic parts. So while we want to gain an understanding of why models don't necessarily match predicted performance or actual performance, I want to spend most of our time discussing how do we change that? What can we do to ensure that our buildings do in fact measure up to what we predict? I'd like to acknowledge Leslie Bew and Tom Reed, if you can raise your hands, as the co-authors of this project. Most of my experience has been on the new construction side of the business, whereas all of theirs, or most of theirs, comes from the existing building stock. And so we got to see or assess this throughout, looking at it from a whole building life cycle approach. So here's our agenda. We just want to touch on whether or not we think sustainability is here to stay, look at prediction accuracy in practice, look over the common approaches both from a new construction side as well as an existing building side, and then really focus in on what are those barriers that prevent us from having great prediction accuracy. And moving on. Okay, so we don't have time to go into these, but essentially if we can focus in on air quality, I guess the long and short of it is we have a lot of data and studies that show things related to air quality. The economic benefits of efficiency and climate change are really increasing to the point where we don't anticipate this sustainability movement going backwards, which may have been in stark contrast to for those of us who lived through the energy crisis of the 70s as an example. So looking at it from an air quality perspective, the bottom line is 142 million Americans experience dangerous levels of air quality in the U.S. alone at some point during the year. And if you extrapolate that, or not extrapolate, but if you look at alternate studies from the World Health Organization, they estimate about 1.3 million people die annually as a direct result of poor air quality. And a lot of this is basically the byproducts of fossil fuel combustion. So this chart basically shows, while we do have all this ever-increasing amount of data that says we should be pushing towards more efficiency, we're still at the I guess at the whim of market forces. And so what this basically charts in the blue is construction spending going back to 2002. And then in the purple overlay is the number of LEED registrations, if we can use that as a litmus test. And we see it basically experienced an exponential rise in 2006, but then, of course, with the construction downturn, we have yet to see if again, LEED registrations are going to pick back up and continue that rise that they were experiencing beforehand. Okay, so here's, we're going to look at two charts. So this particular chart looks at predictions in a new construction project. And basically, if the data point is on the line, the prediction was equal to the measured values. If we're above the line, then we have a building that performed better than anticipated. And then below the line, we have buildings that were underperforming what we predicted. And so the main takeaway here is that we have scatter about the mean. And then we're going to compare this in this chart to an existing building process. So we're using slightly different metrics. We're looking at cost in this example. And the takeaway here is that we have no data points that are above the line. And what that would basically say is that we have energy projects that were implemented that are not achieving the cost savings that were projected or promised. So the takeaway here is that from an existing building approach, we're really good at making sure that we're erring on the conservative side of things, and our scatter does not typically exceed what we predict. So we decided to dive in. Well, what are the different approaches or workflows that possibly lead to this? So we'll go into this chart. It's a little better to look at. So on the top, you basically have a typical design phase approach. So you have design teams who start with the basis of design, and they push through schematic documents, design documents, and construction documents. And then below that, we have the analyst's work. And this is basically meant to show a feedback loop where we start with a lot of alternatives that we're looking at the beginning. We have very little detail, and so we're making a lot of informed assumptions. And we come up with a lot of parametric results, and we're feeding those back to the design team, hopefully to improve the design as they progress through later phases of the design process. And we do this iteratively through each phase, so finally at the end, hopefully we have all the details we need. We're not looking at any more alternatives, and we're making very few, if any, assumptions, and we're getting the final answer. So let's say we're 20% better than code in our final configuration. The existing building approach is a bit different, and essentially it starts differently in that an energy concept is sold to a prospective client, and then once that concept is sold, an analyst will come in and really put numbers to that, and so at this point the analyst takes over, and they're going in and finding the details they need to complete the analysis, and they're making some assumptions, of course, but you come up with results, and then you have to go back to the building owner, and you present them with an array of options, and then the building owner has to decide, well, which one of these options makes most sense to us and meets our goal. Maybe it's carbon emission reductions if you're looking at a company like Google, or maybe it's purely ROI. But this process may iterate several times before something is finalized. And then those decisions are translated to a designer in a spec requirement, for example, and the designers then have to make sure that they design something that is consistent with what the analyst is dictating and what's consistent with the owner's goals. And then perhaps the biggest difference between the existing building process and the new construction process is this results and verification component. If you have an analysis firm that's on the existing building side, they have much more of a vested interest in ensuring that what they predict is actually delivered. And so you have this feedback loop that usually does not occur on the new construction side. So what are the common pitfalls that are experienced from both new construction or an existing building process? Since this is kind of focused on the analysis end, we'll fully acknowledge that underqualified team members can exist in any stakeholder, be it owners who aren't focused on efficiency, designers who aren't versed in the strategies that are being applied, but we'll focus on analysts for this discussion. You can always have a lack of design detail that allows installations to go in perhaps not as intended, and we're not helping ourselves by not going back through and verifying our installations with red lines. And we can't expect commissioning agents to catch all of the errors that may occur. Communication breakdown is often a big problem, and what we're referring to specifically is when things change at the design level or even in the field that don't get conveyed back to the analyst to incorporate into the analysis. And that can often happen even in the value engineering process, where the final model has perhaps already been submitted to either code authorities or the owner, and changes still get made after the fact. And project team accountability is more applicable to the design process rather than the existing building process. And what that speaks to is essentially, we as designers, we issue our drawings and then we're done. We move on to the next project. It goes back to that vested interest idea. We're not often held accountable for things that may lead to poor performance after the building's been turned over. So how can we correct this? Underqualified team members, again, focusing on the analyst, what we're recommending is that when choosing an analyst, and we can take some notes out of the lead book, and basically what we're advocating is that your analyst should have at least 2 projects of similar scope in their back pocket to refer to, and we're focusing more on system complexity rather than building area as example. And the firm should have a documented QC process that includes at least 1 peer review, just as a matter of a good practice. And if they don't have this, that is an indication that perhaps analysis is not really the focal point of this particular group. And no dual hat simply means that we don't want our designers also having the responsibility of analysis. Obviously, there's a conflict of interest there. And then we have a number of third-party certifications that are indicators of basically what we know in the field. So corrective measure 2, integrated design and operations, we basically identified 5 keys. So keeping the analyst in the loop we discussed, making sure that those design changes are fed to that consultant. One big one is positive confirmation of your sequence of operations. We think it's a good idea to make sure that your analysts are pairing up with your engineers and discussing control sequences in a positive manner as early in the design phase as possible, because essentially what we've seen over and over when we looked at a lot of case studies was that the controls are either absent in the worst case scenario, or they're generic from the perspective that they may not apply to the systems that were installed. And so red lines, we need to be doing those. Installer feedback, we need to be making sure that we're having an open line with installers, so if they have questions, they feel like they can come to us to make those changes. And then on the operator side of the equation, we need to make sure that operators have the training they need to run the equipment that we've specified. Building commissioning is mandatory. It's an extra layer of QC, and we're not going to belabor that point. Smart M&V. A lot of times M&V will get value engineered out of the project, and one thing that we can do is ensure that we're advocating for it and basically highlight the risk. And so we can go back to that first chart that I mentioned and see how much that data point deviates from the line, and basically tout the fact that there's a cost involved with that, and that cost has a risk. And so what we can do is use our analysts to identify what are those critical energy efficiency nodes and allocate our M&V resources accordingly so that we're capturing at least those critical nodes. And then finally, again, this is more for the operator side, but we need to try to make sure that we're pushing design teams and even facility owners who we often have opportunity to work with, that the operator training is as important as all the emphasis that is put on design team members, and that if our operators don't have the skills necessary to operate this high-end equipment, what's going to happen is that they're going to override systems or controls, and you're going to lose performance gains that were built in. So in conclusion, basically we just want to make sure that we understand that mistakes can occur throughout the life cycle. There's no magic bullet that's going to fix everything, but with that, we can focus on ensuring that our analysts are well qualified to perform the function that they're doing. We can emphasize that building operations are equally as important as the design side. We can push for building commissioning, and we can also push for appropriate use of M&V. And then finally, again, to reiterate, we want to make sure that our operators are getting the support they need to operate our buildings as we've intended them to operate. That's it. Thanks.